Section 9 of The Science History of the Universe, Volume 2, Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by James Curran. The Science History of the Universe, Volume 2, edited by Francis Rothweiler. Geology. Chapter 5. Development of Modern Knowledge. Part 1. With Hutton's work as a basic point, geology took new life. The theory in the main was sound. It remained but to classify the results of the past and to prepare for the reception of the observations of the future. The 19th century witnessed the great development of the process of the Earth's formation from stratigraphical geology set forth. Jean-Baptiste Pierre-Antoine de Monet, Chevalier de Lamarck, 1744 to 1829, came from an ancient but somewhat decayed family and was born in a village of Picardy as the 11th and youngest child of the Seigneur de Barne. The earlier part of his career was devoted first to soldiering, then to botany, and then to zoology. Though Lamarck wrote little on geology, the extent to which he had pondered over the problems of the science, which in his time had hardly taken definite shape, is well illustrated by the little volume which he published in 1802 under the title of Hydrogeology. He recognized that nothing can ultimately resist the alternating influence of wetness and drought, combined with that of heat and cold, and that the disintegration of mineral substances by these atmospheric conditions prepares the way for the erosive action of running water in all its various forms. To him, it was clear that every mountain which had not been erupted by volcanic action or by some other catastrophe had been cut out of a plain, so that the mountain summits represent the relics of that plain, save in so far as its level has been lowered in the general degradation. He admits that in many mountains, the component strata were often vertical or highly inclined. But he will not in that account believe in any universal catastrophe, such as has been demanded by many previous writers, and was still loudly advocated in his own time by his fellow countryman, Cuvier. Lamarck conceived the ocean basin to owe its existence and preservation to the perpetual oscillation of the tides, and partly also to the general westerly movement of the water. He supposed the tidal oscillation to be a gigantic force, which has actually eroded the basin and now prevents it from being shallowed, through the deposit of land-derived sediment, by continually scoring this sediment out and casting it along the more sheltered shores of the land. No one before his time had been able to follow so clearly the successive stages through which organic remains pass until they become crystalline stone, presenting no trace of their original organic structure. During the last 10 years of his long life, he suffered from total blindness and had to rely on the affectionate devotion of his eldest daughter for the completion of such works as he had in progress before his eyesight failed. The world is becoming more conscious now of what it owes to the genius of this illustrious naturalist. Among those students of science who have the most reason to cherish his memory, geologists should look back gratefully to his services in starting the science of paleontology, in propounding that the doctrine of evolution, and in affirming that the great insight of some of the fundamental principles of modern geology. Georges Cuvier, 1769 to 1832, a French naturalist and founder of the science of comparative anatomy, effected a great and noble advance in the science of paleontology. It is to Cuvier that the world owes its first systematic application of that science of comparative anatomy, which he himself did so much to place upon a sound basis, to the study of the bones of fossil animals. He demonstrated that extinct animals could be reconstructed from fragmentary remains by applying the law of correction of growth. It is true, as pointed out by Professor Huxley that he placed more confidence and security in this law than its empiric nature and exceptions would justify. Cuvier, in his work in the geology of the Paris Basin, was greatly assisted by his friend Alexandre Brongniart. Brongniart was early trained in scientific pursuits. In 1807, he published a treatise on mineralogy, which became a standard work. He became professor of mineralogy at the Jardin des Plantes, and in 1808 appeared the work on the Paris Basin. Cuvier and Brongniart drew up a systematic table of the succession of the stratigraphical horizons in accordance primarily with the sequence of the deposits in the ground and with the particular fossils characterizing each group of deposits. The varieties of rock and the thicknesses and distribution of the different deposits were also fully considered and carefully mapped. Omalis de Holoy, 1783 to 1875, the Belgian geologist, made an examination of the formations of the Auvergne, Valais, and in parts of Italy and Germany, and in all cases proved conclusively that the fossil remains had been embedded in the deposits of freshwater marshes and were not remains which had been accidentally swept into marine deposits. The Belgian geologist supplemented the observations of Cuvier and Brongniart with great success. Early in his career, de Holoy had regarded the position of the strata, their horizontal, slightly or highly inclined, or vertical position, of great importance in determining the age of the strata. He thought the horizontal strata corresponded to Werner's Floats formations, and all inclined strata to Werner's transitional formations. But his subsequent visit to the Alps and Ural Mountains caused him to modify these views. The fearful earthquake which destroyed Lisbon in 1755 was made the subject of a large number of scientific inquiries into the causes of earthquakes. William Stukeley's theory, attributing earthquakes to electrical disturbances, gained a certain amount of support abroad. Another Englishman, Reverend John Marshall, suggested that sudden expansion of vapors enclosed in fissures and cavities in the Earth's crust caused earthquakes and volcanoes, the upheaval of mountain systems, and the deformation of rocks. In 1760, he published a series of observations on earthquakes in mountain structure. This paper was accompanied by an ideal section through a mountain system, showing a central core composed of the crystalline massive rocks on either side in succession of uptilted and upheaved strata covered in their turn by younger, slightly tilted or horizontal deposits composing the neighboring plains. Marshall, however, did not draw any general conclusions, yet he deservedly ranks as the great pioneer of the modern science of seismology. Another English observer was John Whitehurst, 1713 to 1788, who published in 1778 an Inquiry into the Original State and Formation of the Earth. This work was the last effort of the fantastic English school of cosmologists. Amid absurd speculations as to the condition of chaos and other equally visionary topics, he wrote well on organic remains and showed that he clearly grasped the stratigraphical succession of the formation in Derbyshire and other parts of England. Quote, "The strata invariably follows each other," end quote, he remarks, quote, "as it were in alphabetical order," end quote. And though they may not be alike in all parts of the earth, nevertheless, in each particular part, how much soever they may differ, yet they follow each other in a regular succession. He was one of the many who were interested in the origin of the basalt pillars of the Giant's Causeway, and who endeavored to interpret their origins. One of the most active and interesting of those who devoted themselves with ardor to the study of the Italian volcanoes was Gatta di Dolomule, 1750 to 1801. His attention was especially drawn to the active and extinct volcanoes of the Mediterranean basin. As far back as 1776, he made an announcement that he had found in Portugal evidence of volcanoes older than certain mountains of limestone, a statement which he supplemented in 1784 with further evidence from Sicily, proving the intercalation of ancient lavas among stratified deposits. Dolomieu confirmed the igneous origin of basalt rock, regarding it as a variety of lava, for the most part associated with submarine eruptions. His name is perpetuated in the name of the Dolomites, given to the beautiful district in South Tyrol, south of the Puster Valley. Elie de Beaumont was another scientific Frenchman who interested himself in mountains. He was one of the most enthusiastic adherents of the volcanist doctrines. Toward the end of an article on mountains, which appeared in the Annals of the French Academy, are a few remarks on mountain structure. Brief although they are, the remarks on the influence of the slow cooling of the earth on surface conformation and the origin of furrows and fissures are at once recognized by a reader of the present day as the starting point of the modern view on mountain structure. Later appeared his 3-volume treatise on mountain systems. He points out that in virtue of the continued cooling of the planet, the radius is shortened and the crust is affected by a general centripetal movement. That is, the volume of the globe becoming less, the crust is drawn in toward the center of gravity. Delisle, meanwhile, had calculated 1,340 meters as the amount by which the Earth's radius had already been shortened. In other words, the Earth's crust in the course of the geological epochs had approached the Earth's center by a distance about equal to the height of Chimborazo or the Himalayas above sea level. William Smith, 1769 to 1839, an English engineer, was the first to recognize the importance of fossils in their full significance as a means of determining the relative age of strata. Born in a country that was unusually rich in fossil remains, he had in his boyhood abundant opportunity of observing and collecting. For 25 years he continued his investigation of all parts of England, entering his observations in colored geographical maps and compiled them from time to time in the form of tables or as explanatory notes to his maps. About 1800, he began the preparation of a geographical map of England and Wales on the scale of 5 miles to 1 inch, which occupied nearly 15 years of his life, and which was supplemented by separate maps of the counties, published in color on 21 sheets. Smith's map is the first attempt to represent on a large scale the geographical relations of any extensive tract of ground in Europe. It was a magnificent achievement and was the model of all subsequent geological maps. For English geography, the publication of the map was the starting point of a new regime. The Geological Society of London conferred upon him the Wollaston Medal, and he well deserves to be called the father of English geology. There is yet another name that deserves to be remembered in any review of the early efforts to group the secondary formations, that of Thomas Webster, 1773 to 1844. As far back as 1811, this clever artist and keen-eyed geologist began a series of investigations of the coast sections of the Isle of Wight and of Dorset, and continued them for 3 years. He clearly defined each of the leading subdivisions of the Cretaceous series and prepared the way for the admirable later and more detailed work of William Henry Fitton, 1780 to 1861, to whom geology is indebted for the first detailed and accurate determination of the succession of strata and their distinctive fossils, from the base of the chalk down into the oolites in the south of England and the neighboring region in France. More particularly, he showed the relations and importance of the greensand formations, his memoirs on which are now among the classics of English geology. The early progress of stratigraphical geology in Britain includes the important influence exerted by the Geological Society of London, which was founded in 1807 to investigate the mineral structure of the Earth. At the time, the warfare between the Neptunists and the Plutonists still continued, but there were many men interested in the study of geological subjects who were weary of the conflict of hypothesis and who would fain devote their time and energy to the accumulation of facts regarding the ancient history of the globe rather than to the elaboration of theories to explain them. A few such inquirers formed themselves into the Geological Society and soon attracted others around them until, in a few years, they had established an active institution which became a center for geological research and discussion, published the contributions of its members in 4 volumes, and eventually was incorporated by royal charter as one of the leading scientific bodies of the country. This society, which has been the parent of others in different countries, continues to flourish, and its publications, extending over nearly a century, contain a record of the original researches which have powerfully helped the progress of all branches of geology. Besides their papers issued by the Society, some of the early members published separate works which greatly advanced the cause of their favorite science. Among these early independent treatises, perhaps the most important was the Outlines of the Geology of England and Wales by W.D. Conybeare, 1787 to 1857, and W. Phillips, 1775 to 1828, which appeared in 1822. In this volume, all that was then known regarding the rocks of the country, from the youngest formations down to the old red sandstone, was summarized in clear and methodical a manner as to give a definite impulse to the cultivation of geology in England. The amount of ascertained fact regarding the structure and history of the earth was every year increasing at so rapid a rate that it became necessary to prepare digests of it for the use of those who wish to be informed on these subjects or to keep pace with the advance of knowledge. Hence arose in different countries textbooks, manuals, and other general treatises. Herein an account was given of the facts and principles of geological science. But of all the English writers of general treatises on geology, the first place must undoubtedly be assigned to Charles Lyell, 1797 to 1875, who exercised a profound influence on the geology of his time in all English-speaking countries, adopting the principles of the Hutton theory, says Sir Archibald Geikie in his Founders of Geology. He developed them until the original enunciator of them was nearly lost sight of. Quote, "With unwearied industry he marshaled in admirable order all the observations that he could collect in support of the doctrine that the present is the key to the past. With inimitable lucidity he traced the operation of existing causes and held them up as a measure of those which had acted in bygone time. He carried Hutton's doctrine to its logical conclusion, for not only did he refuse to allow the introduction of any process which could not be shown to be part of the present system of nature, he would not even admit that there were any reasons to support the degree of activity of geological agents to have ever seriously differed from what it has been within human experience. He became the great high priest of uniformitarianism, the creed which grew to be almost universal in England during his life, but which never made much way in the rest of Europe, and which, to its extreme form, is probably now held by few geologists in the country." End quote. Lyell's Principles of Geology will, however, always rank as one of the classics of geology, and must form an early part of the reading of every man who would wish to make himself an accomplished geologist. The last part of his work was ultimately published as a separate volume, with the title Elements of Geology, in which a large space was devoted to an account of the stratified fossiliferous formations. This treatise, diligently kept up to date by its author, continued during his lifetime to be the chief English exposition of its subject and the handbook of every English geologist. End of section 9.